In this last lecture on algebra, we're going to see what was an earth-shattering idea, the idea of connecting algebra with geometry, how you could actually see an equation, how you could actually visualize an equation. Before we go into that, let's talk a little bit about polynomials. Okay, here are some examples of polynomials. 8x cubed minus 5x squared plus 4x plus 7. X to the 10th plus 9x squared minus 3.2. And so on and so on. Here, x plus 7, even 7 by itself, is a polynomial. We say that the degree of a polynomial is the largest exponent in the polynomial. So for instance, the first polynomial has degree 3 because of the x cubed term. The second polynomial has degree 10 because of the x to the 10th term. The next polynomial has degree 4. X by itself has degree 1, so does x plus 7. The constant polynomial has degree 0. You could think of that as 7 times x to the 0. And when dealing with polynomials, all the exponents have to be whole numbers that are at least 0. So we're not allowed any negative exponents. We're not allowed any fractional exponents. First, let's review the ever-important law of exponents. X to the a times x to the b is equal to x to the a plus b. That should be part of our algebraic toolbox. Now, why is that? I mean, initially you might think x to the a times x to the b. Why shouldn't that be x to the a times b? Well, let's do an example. If we look at x squared times x cubed, x to the 2 times x to the 3, the law of exponents says that that's x to the 2 plus 3 equals x to the 5th. Why? Well, if you look at x squared, that's x times x. X cubed is x times x times x. So when you multiply them together, you have x times x times x times x times x. How many x's are you multiplying? 5 of them, 2 plus 3. That's why we have x to the 5th. Now the law of exponents is so handy, we want it to be true not just for positive integers like the example we have here, we want it to be true for other things as well. So for instance, I want it to be true when the exponent is 0. That is, I want x to the a times x to the 0 to be x to the a plus 0. But a plus 0 is a. So that says that x to the a times x to the 0 is equal to x to the a. If you want the law of exponents to work there, then that forces x to the 0 to be what? To be 1. So that x to the a times x to the 0 is still x to the a. That's the reason why x to the 0 power is 1. It's also a reason I'd mentioned in an earlier lecture. If you're multiplying 0 things together, I always felt that that's a good reason for that being 1. If you're adding 0 things together, it's 0. But when you're multiplying 0 things together, it's 1. A typical polynomial of degree n will look like this. A times x to the n plus b x to the n minus 1 plus c x to the n minus 2 and so on. Where the a, b, c's, all of the coefficients that we're seeing, that's what they are called, the coefficients a, b, and c, can be any real number that you want. They could be integers, they could be fractions. The only requirement is if it's of degree n, the coefficient behind the x to the n term can't be 0. A cannot be 0, otherwise it wouldn't have degree n, it would have a smaller degree. We say that a polynomial equation looks like y equals ax to the n plus bx to the n minus 1 and so on. This is called an nth degree equation. Okay, now we're ready for the moment that I told you about at the beginning, how to see an equation. Let's start by looking at the simplest equations, first degree equations, that is, linear equations. And we're going to see why we call these linear in a moment. Let's take one of the simplest linear equations, y equals 2x. What should that look like? Well, let's plug in some values. When x is 0, y is twice 0, which is 0. When x is 1, y is twice 1, which is 2. When x is 2, y is 4. When x is 3, y is 6. Notice every time you add 1 to x, you add 2 to y. Okay? If we were to plot these points on what's called the Cartesian plane, that's where I have an x-axis that goes horizontally and a y-axis that goes vertically. By the way, this is called the Cartesian plane because it was discovered by the mathematician and philosopher René Descartes. He actually discovered this while in the hospital. We should all have such productive idle time. Anyway, let's plot the points 0, 0, 1, 2, 2, 4, 3, 6. So for instance, when I'm plotting 3, 6, that means I'm going 3 to the right on my x-axis, and I'm going 6 up on the y-axis. And where those coordinates meet, that's the point 3, 6. If you now connect the dots and don't expect any surprises, then you're going to have a line that goes through all of the points. And that's why we call it a linear equation. And again, we see every time you increase x by 1, y is going to increase by 2. If you decrease x by 1, y is going to decrease by 2. Okay, let's move this equation up, literally, by changing it from y equals 2x to y equals 2x plus 3. What does that do to your graph? Well, all it does is it takes all of those same points that we had before, and now it adds 3 to everything. And so y increases by 3 everywhere. So you can see this line lifting up. It's parallel to the old line, but now it's higher than that old line by 3 everywhere. Okay, so that's the graph. We call this the graph of our function, the graph of our equation, y equals 2x plus 3. And we give names to the coefficients behind the x term and the constant term. So the y equals 2x plus 3, we call 2 the slope of the line, and we call 3 the y-intercept of the line. Why do we call 2 the slope of the line? That tells you how much your line is increasing. If x increases by 1, then y increases by 2, just like it did before. If x decreases by 1, then y decreases by 2. Heck, if x increases by 3, then what will happen to y? Y is going to increase by twice 3. It's going to increase by 6. If x increases by 32.7, then y is going to increase by twice that, 65.4. If it decreased by 32.7, then y will decrease by 65.4. So that's what the slope does. The y-intercept does exactly what it says. It's where that line crosses the y-axis. Where does it cross the y-axis? At the point 0, 3. And therefore we say it intercepts the y-axis right there at the point 0, 3. The first coordinate will always be 0, and the second coordinate in this case is 3. That's why we call 3 the y-intercept. If we were to generalize this, let's say looking at the equation y equals mx plus b, then what do we have here? The slope of this equation is m, and the y-intercept is b. Let's deal with the y-intercept first. That means that where that line is going to cross the y-axis is when x is 0 and y is b. The slope being m tells us that if x increases by 2, then y will increase by m times 2, or 2m. If x increases by 3, then y will increase by 3m. If x increases by 32.7, then y will increase by 32.7 times m, the slope. If x decreases by 32.7, then y will decrease by 32.7 times m. Let's draw some of these graphs just to get a picture of them. Okay, I'll draw several of them at once. So for instance, y equals 2x plus 3, that's already there. Suppose we were to look at y equal 0.5x minus 4. All right, what does that tell us? It tells me that my slope is not 2, it's a half. So that line is not going to increase nearly as quickly as 2x plus 3. Where does it intercept the y-axis? At the y-intercept, at negative 4. So if we plot that point, the y-intercept down there at 0, negative 4, and every time we increase x by 1, now y only increases by a half. All right, let's look at another line. Here's the line y equals negative 4x plus 10. Where does it intercept the y-axis? Way up at the top at 10. And now for every increase of x by 1, that function decreases at a rate of 4. So every increase of, if you increase x by 10, then y is going to decrease by 40. Here's another line that's got a very big negative slope, even steeper. Y equals negative 8x minus 2. How about a line with 0 slope? All right, that would be like, say y equals, just to pick a random constant, 1.618. If I take 1.618 and draw that line, then we see that's what a line of 0 slope looks like. By the way, that's still called a linear equation, even though that's an equation of 0th degree. Finally, let's look at a line of infinite slope, right? Suppose I just have the equation x equals 2. That says x equals 2 no matter what y is. Y can be 0, 1, 100, negative pi, whatever. X is always going to be 2, and that's going to look like a vertical line. Okay? Let's now solve a geometry problem using algebra. So here's a question. Where do these two lines cross? Okay, let's say one line looks like y equals 2x plus 3, and the other line is y equals negative 4x plus 10. Okay, so we've drawn both lines on our screen, and now we say, well, where do those lines cross? Well, we're about to solve, really, a linear equation. Where they cross, y is both equal to 2x plus 3 and y is equal to negative 4x plus 10. Let's then set those two equations equal to each other. That is, set 2x plus 3 equal to negative 4x plus 10, because where they meet, those two things are going to be equal. Now we'll add 4x to both sides. We'll subtract 3 from both sides. We're getting good at this. That gives us 6x equals 7. Solving for that, it says x is equal to 7/6. And what's y equal to at that point where they cross? Well, take your pick. Y is equal to 2x plus 3 or negative 4x plus 10. Let's use 2x plus 3. So y is equal to 2 times 7/6 plus 3. That's equal to 7/3 plus 3. That's 7/3 plus 9/3 is 16/3, 16 over 3. Just to check it out, just to verify our solution, when x is equal to 7/6, where is it at negative 4x plus 10? Well, negative 4 times 7/6 is negative 28/6 plus 10, that's 60 over 6. Add those together, we get 32 over 6, which is equal to 16 over 3. So that checks out. Here's a more practical question. Suppose you were offered 2 different phone plans for your telephone, and you want to decide which of those plans is going to give you, save you more money in the long run. One of the plans charges you $10 flat fee plus 15 cents for each minute that you use. Another plan offers you $20 flat fee plus 10 cents for every minute that you use. Which plan should you use? Well, it depends if you use your phone a lot or you don't use it that much. If you use it a lot, then maybe you'll want to pay the $20 flat fee for a lower 10-cent rate. If you only use your phone a little bit, well, then you'll probably want the rate that's 15 cents a minute with a smaller flat fee. But to find out where that critical point is, where you change from not using it enough to using it too much, we're going to set these two equations equal to each other. So the equation that the first thing, the bill, let's call the bill B, is equal to $10 plus $0.15 times m being the number of minutes that you use. In the second equation, the bill that you pay will be $20 plus a tenth of a dollar, 10 cents per minute. So a tenth of a dollar times every minute that you use. So the two equations that we're faced with are B equals 10 plus 0.15 m and B equals 20 plus 0.10 m. Setting those two equations equal to each other, then we can solve that, right? 10 plus 0.15 m equals 20 plus 0.10 m. Putting the m's on one side and the constant terms on the other says 0.05 m equals 10. Multiply both sides by 20 to get that m equals 200. So if the number of minutes that you use is 200 minutes or more, then you're going to want the plan that has the lower per minute plan, the $20 plus 10 cents a minute. If you use under 200 minutes per month, then you're going to want the first plan, the one that had $10 plus 15 cents a minute. And if it was exactly, not that you'll ever know in advance how much exactly you're going to use, then either plan would offer the same. Okay? And again, it's worth verifying that you'll get the same amount either way. In this case, if you went 200 minutes, whether you use the first plan or the second plan, you would wind up with $40 as your bill. And that corresponds to the point where those two lines cross, is the point 240. Let's graduate from first degree equations to second degree equations. Say we look at y equals x squared. That's the simplest of second degree equations. This is called a parabolic equation. The graph that's drawn looks like this. It's called a parabola. Let's play around with this parabola. Let's make some changes to our equation and see how that changes our graph. For instance, what if we look at y equals 2x squared? All right, we see y equals x squared in red. What about y equals 2x squared here in blue? Then that says y is going to increase much, much faster. Okay, so that's why it's going to be on the inside track from y equals x squared. So it still has the same basic shape, but it increases much faster. How about still starting with the basic y equals x squared here? Suppose we wanted to look at y equals x squared plus 2. Well, all you've done here is you've increased y by 2 everywhere you found it. Right? So what used to sit there on the x-axis has now raised above the x-axis by 2. So that's y equals x squared plus 2. How about y equals x minus 2 squared? That's going to shift your parabola, but will it shift it 2 units to the right or shift it 2 units to the left? The answer is it shifts it 2 units to the right. That is y equals x minus 2 squared. And to see why it shifts it 2 units to the right, we look at what happens when x is equal to 2. When x is equal to 2, then y is equal to 0 squared, which is 0. So that says that the x-intercept of that parabola, that we touch the x-axis at the point where x equals 2. So that means you shift it to the right. If you wanted to shift it to the left, then you would look at y equals x plus 2 squared. Notice if you took, say, y equals x minus 2 squared, what we had before, and now we subtract 2 from that, that's going to bring that whole parabola down. It looks like x squared minus 4x plus 4 minus 2, which is x squared minus 4x plus 2. That looks like a pretty generic quadratic equation, right? Y equals x squared minus 4x plus 2. It just shows you that this, even though it looks different from the equations we've seen before, is nothing more than a shifted parabola in disguise. In fact, any quadratic equation is nothing more than a shifted parabola. For instance, y equals x squared minus 8x plus 10, basically by using the technique of completing the square, that we can rewrite that as x squared minus 8x plus 16 minus 6. I just replaced 10 with 16 minus 6 there. But now the thing I have in parentheses is equal to x minus 4 squared. So that says y is equal to x minus 4 squared minus 6. It's just a parabola shifted to the right by 4 and then lowered by 6. Now, my reason for going into this in such detail is so that you see that no matter what second-degree equation you have, you're going to have a parabola that's going to intersect the x-axis how many times? Well, in the pictures on our screen, it's intersecting it twice. It's possible for it to intersect it just once. Take our original equation, y equals x squared. That only intersects it once. And it's also possible for it to intercept it 0 times, right? Take an equation like y equals x squared plus 2. That's not going to intersect it at all. But the lesson here is that any second-degree equation is going to intersect the x-axis 2 times, 1 times, or 0 times. Let's look at third-degree equations. I'll give you the third degree right here, right? Y equals x cubed. That has a graph that looks like this. Okay? Y equals x cubed plus 4x squared plus 4x looks like that. Y equals x cubed minus 7x plus 6 looks like that. In all these pictures, you see, I'm not going to give you a rigorous proof here, but you see that the cubics cross the x-axis at most 3 times. It could do it twice or once, or, well, they have to do it at least once. They can't go 0 times, but they have to cross the x-axis no more than 3 times. Here's the general rule, okay? Fundamental theorem of algebra, so you know it has to be important. In fact, this theorem was so important and so non-trivial to prove that this was in the doctoral dissertation of Gauss. Remember him as from the young boy who added up the numbers 1 to 100? You know, now he goes to college and he proves the fundamental theorem of algebra. Fundamental theorem of algebra says the graph of a polynomial of degree n will intersect the x-axis at most n times. Just like we saw it when n is 2 for the quadratics and n was 3 for the cubics. In general, an nth degree equation can intersect the x-axis at most n times. Equivalently, if you have a polynomial of degree n, let's call that p of x as the polynomial of degree n, then the number of solutions to the equation p of x equals 0 is at most n. So for instance, if you wanted to solve the equation 2x to the 10 minus 7x to the 4th plus 5x plus 9 equals 0, then even if we can't come up with a nice equation for the answer, what the fundamental theorem of algebra tells us is there are at most 10 solutions to that problem. Well, so far we've been dealing with polynomials, and polynomials have exponents that are non-negative numbers. Let's look at some other kinds of exponents. They won't be polynomials anymore, but we should still look at them. Like for instance, what about x to the negative 1? What should x to the negative 1 mean? Well, if we want the law of exponents to be a law for all numbers, we want x to the a times x to the b to be x to the a plus b, then what would happen if I plugged a equal negative 1 and b equal positive 1 into the law of exponents? That would tell us that x to the negative 1 times x, that is x to the negative 1 times x to the first power, is x to the negative 1 plus 1, which is x to the 0, which is 1. In other words, x to the negative 1, when multiplied by x, gives us 1. What does that tell me about x to the negative 1? It tells me that that means that x to the negative 1 is the reciprocal of x. That is, x to the negative 1 is equal to 1 over x for any x not equal to 0. You know, even the law of exponents can't violate the law of dividing by 0. So x to the negative 1 is 1 over x for all x not equal to 0. So for instance, 3 to the negative 1 is 1/3. 9 to the negative 1 is a 9th. Negative 7 to the negative 1 is 1 over negative 7. That is negative 1/7. But 0 to the negative 1 is forever undefined. Some people say infinity, but you could just as well make a case for negative infinity. Just don't try it. 0 to the negative 1 is undefined. How about other negative exponents? Like what about 3 to the negative 2? 3 to the negative 2 is 3 to the negative 1 minus 1. which is 3 to the negative 1 times 3 to the negative 1, is a third times a third, which is a third squared, which is 1/9. In other words, x to the negative 1 is 1 over x. X to the negative 2, by the law of exponents, is going to always be 1 over x squared. And by the same logic, x to the negative 3 is going to be 1 over x cubed. And x to the negative n will be 1 over x to the n. Okay, these aren't polynomials, but it's worth knowing. Let's take a look at their graphs. Here's y equals 1 over x. Okay, again, you see as x gets closer and closer to 0, from the right, 1 over x is getting closer and closer to infinity. And on the left side, as x gets closer and closer to 0, then y is going to negative infinity. Here's a graph of y equals 1 over x squared. How about fractional exponents? What should 9 to the 1/2 mean? Well, let's use the law of exponents again and see what we want it to mean. All right, what if I let x to the a times x to the b be x to the a plus b, even when a and b are fractions? So for instance, when a and b are both a half, what is 9 to the 1/2 plus a half? Well, by the law of exponents, it's 9 to the 1/2 times 9 to the 1/2. On the other hand, it's also equal to 9 to the 1. And 9 to the 1 is 9. So that tells me that 9 to the 1/2 times 9 to the 1/2 is equal to 9. In other words, 9 to the 1/2 is equal to 3. Oh, now, careful here. You might say, hey, Professor Benjamin, you said 9 to the 1/2 is equal to 3. Couldn't 9 to the 1/2 also be equal to negative 3? I mean, after all, negative 3 times negative 3 is also 9. Well, the problem is, if we want this to be well defined, we want 9 to the 1/2 to just be one thing, we're going to make the choice of making it the positive thing. I know we're discriminating against that poor negative number, but mathematicians define 9 to the 1/2 to be equal to 3, not negative 3. In general, x to the 1/2 is equal to the square root of x, or some might say, to be more explicit, x to the 1/2 is equal to the positive square root of x. So for instance, the square root of 9 is 3. The square root of 16 is 4, not negative 4. The square root of 2 is just the square root of 2, but numerically it's about 1.414. Okay? The square root of 1 is 1. The square root of 0 is 0. Here's the graph of y equals square root of x. Notice that we only drew the graph here to the right of x equals 0, because to the left of x equals 0, we'd be looking at the square roots of negative numbers, which we're not quite ready to handle yet. So we'll just say that's undefined for now. How about x to the 1/3? What should that mean? Well, by the law of exponents, x to the a times x to the b times x to the c equals x to the a plus b plus c. So x to the 3rd times x to the 3rd times x to the 3rd is x to the 1/3 plus 1/3 plus 1/3. That's x to the 1, which is x. Therefore, x to the 1/3 is the cube root of x, denoted by, looks like a square root of x with a 3 on the outside. So for instance, the cube root of 8 is 2. The cube root of 27 is 3. The cube root of 2 is just the cube root of 2, but numerically it's about 1.259. Here's the graph of the cube root function. Let me show you a couple of other important graphs that are worth knowing. For instance, here is the equation of a circle. Here's the unit circle. The circle centered around the origin, that's the 0, 0 point, the origin, with radius 1. And that equation looks like x squared plus y squared equals 1. You could rewrite that as to say y squared equals 1 minus x squared, or technically you might say the top half of the circle is y equals the square root of 1 minus x squared, and the bottom half of the circle is y is equal to the negative of square root of 1 minus x squared. But it's cleaner to just put the top half and the bottom half together to get the nice equation x squared plus y squared equals 1. Here's a bigger circle, or a more general circle. Instead of intercepting the x and y axis 1 away from the origin, suppose we intercepted it r away from the origin, then that has the equation x squared plus y squared equals r squared. In fact, this can be derived from the Pythagorean theorem, which we'll talk about later. Here are some other examples. X squared plus y squared equals 10 squared, or 100, would be a circle of radius 10. We can shift our circle. If we say moved it over to the right, and that would look like the quantity x minus 2 squared plus y squared equals 10 squared. Right? If we then took that and pushed it up 1 by 1 unit, it would look like x minus 2 squared plus y minus 1 squared equals 10 squared. These are all equations of a circle. So let's recap what we've seen here. We've seen polynomials, what they are, how to graph them. We talked about the fundamental theorem of algebra, and we talked a little bit about negative and fractional exponents. So let me end with a little story here about a horse that once learned how to do arithmetic. His name was Clever Hans, and the people in the crowd would shout out arithmetic problems to it, and it would, put out its hoofs and pound 5 times, and the answer would be 5, and the horse was correct. And they would give it more complicated problems, like multiplication problems, and it took him a little longer, but he was able to do it. They tried him on algebra problems. He was able to do those. Finally, somebody threw out a problem in analytic geometry, and the horse couldn't do it. In fact, it got so crazy, the horse just fell to pieces and died. And the moral of that story is never put Descartes before the horse.